In this screencast I'm going to look at the method of Lagrange multipliers, and this method is often used to find the maximum or minimum value of something subject to one or more constraints. And I'm going to illustrate this method with the example that I have typed up here. Find the minimum distance from the origin to the intersection of xy equals 6 with 7x plus 24z equals 0. So I'm in 3 dimensions here, and what I'm looking for is the point in the 3D space x, y, z, such that the distance from the origin to that point is minimized. So if I want to look at the expression I need to minimize, it is the square root of x squared plus y squared plus z squared. That's the Pythagorean distance from the origin to the point x, y, z. But in fact that is slightly more complicated than it need be, because if I want to minimize that function, then the point at which it is minimized will be the same as the point at which the function x squared plus y squared plus z squared is minimized. You can have a think about why that might be. So in fact I may as well just minimize x squared plus y squared plus z squared, and that's a simpler problem. And I have to do that subject to the 2 constraints that I'm given. And let me now illustrate the method of how we do this. What we do is we define a function to be equal to, first of all, the expression that we are trying to minimize or maximize, if that were the case. And then we add on a constant multiple of the first constraint, where we've rearranged the first constraint if necessary so that we have an expression involving the variables equal to a constant. And in fact that's already given. I've just got xy here because xy is equal to the constant value of 6. If I wanted to, I could subtract the 6 over to the left hand side of that first constraint so that I have xy minus 6 equals 0, and that would be perfectly acceptable as well, or indeed any other expression where I have a function of x and y equaling a constant. You'll see when we come to work on this in a moment, when we do the derivatives, that it doesn't matter what we have for the arbitrary constant because it's going to disappear. So in fact I'm going to remove that extra term and just have lambda 1 times xy. Similarly with the second constraint, 7x plus 24z is a constant, it equals 0, so that will do for the second term. And now what I do is I differentiate this function f with respect to x, y and z partially. So if I do the first one, I get 2x plus lambda 1y plus 7 lambda 2, and I set these derivatives equal to 0. So there's my first one, and I do the same with respect to y, so I get 2y plus lambda 1x equals 0, and I do the same with respect to z. 2z plus 24 lambda 2 equals 0. And in fact I'll just divide through by 2 before I continue with that, just to make it slightly simpler. So I have 3 equations here, and if I in fact scroll back up a little bit, I have 2 more equations. That's equation 4, xy equals 6, and equation 5, 7x plus 24z equals 0. Those are the constraints. So in total I have 5 equations here and 5 unknowns, x, y, z, lambda 1 and lambda 2. And what I need to do is solve these 5 equations. I'm not actually interested in the values of lambda 1 and lambda 2, so I can ignore those and eliminate them. It's the values of x, y and z that I want. And what I suggest you do, if you can, is stop this screencast now and try to find the values of x, y and z which satisfy these equations. I'm going to do that now. I'm going to solve equations 1, 2, 3, 4 and 5. And in fact, sorry, I'll keep them all up there for the moment. There's plenty of different ways of doing this, and most of the time you need to just spend a few moments thinking about the best way to proceed. And the way I'm going to proceed may well not be the best way, and it may well not be the way that you thought of doing it, but it's the way that I would actually approach this problem. And what I'm going to do is I'm going to look at equation 1, and I'm going to try and get everything in terms of x. And then I will just have an expression, hopefully, in terms of x, and I can rearrange that and make x the subject. So I need to work on this. For example, this y term here from equation 4 is just going to be 6 over x. So that will be in terms of x. I also need to get this lambda 1 term here, and that's going to come from equation 2. So lambda 1 is minus 2y over x. So it is minus 2 over x times by y, which itself is 6 over x. So that is that middle term in equation 1 worked out in terms of x. I now need to do the same for the third term. I need a lambda 2. So from equation 3, I have lambda 2 is minus z over 12. And from equation 5 up at the top, z is minus 7x over 24. I should point out that the numbers aren't that pleasant here, but in fact everything will cancel quite nicely at the end, so it's not as unpleasant as it may actually appear. So let me now rewrite equation 1 just in terms of x. What I've got is 2x plus lambda 1, which is 12 over x squared, times by y, which is 6 over x, plus 7 lambda 2, which is actually 7x over 12 times 24. And that equals 0. And it's in fact easier, you'll see, if I don't multiply these numbers together too much. Everything's going to cancel if I just try and keep them factorised. So now the problem is simply to find the value of x. And what I'm going to do here is multiply through by 12 times 24 times x cubed. So the first term will be 2 lots of 12, which is 24, times another 24, times by an x cubed by an x, which is an x to the 4. The next one, I've got, the x cubed will cancel, and I've got a 12 times a 6 times a 12 times a 24. So I'll sort that out in the next line. And then here I've got 7 squared times by x to the 4, and I still have 0 on the right hand side. So what I've got here is, gathering together the terms, I've got x to the 4, a 24 squared plus a 7 squared, equaling 12 lots of 6 of 12 of 24. And if you think what 24 is, it's 2 lots of 12. So actually what I've got here is 12 times 12 times 12 times 12. I've got 12 to the 4. And now, on the next line, you can obviously resort to the calculator if necessary, but I've got a Pythagorean triple here. This is, I don't know if you remember these, there's a 7, 24, 25 triangle, in the same way as there's a 3, 4, 5 triangle. So actually, 7 squared plus 24 squared, check it if you're not sure, is 25 squared. So you can see that this has in fact simplified to something fairly straightforward. And if I square root, I get plus or minus 12 squared over 5. And we only want real values of x, y and z, so we can ignore the negative. We want x to be real. But x certainly can be negative, so I can square root again. And if I square root again, and in fact, I'm sorry, I can see I've made a mistake here. If I square root here, I hope you can see that. If I square root, I'll write it here, 12 to the 4 over 25 squared, I actually get 12 squared over 25. So that should have been a 25, and I only had a 5 there before, so I apologise for that. So x squared should be 12 squared over 25, and what that means is that x is plus or minus 12 over 5. And we could have either answer for that, so we need to work with both. And all we now have to do is work back up and have a look at what y and z should be when x is 12 over 5 and then minus 12 over 5. And I'll leave you to check that because those should be okay. If x is 12 over 5, you should see that y ends up being 5 over 2 and z ends up being minus 7/10. And if x is minus 12 over 5, the signs just change. So y is minus 5 over 2 and z ends up being plus 7/10. So both of these 2 points are acceptable solutions to the problem of where is the point at which the distance from the origin to the point is minimised. And we've got 2 possible points. And the minimum distance is, and I'll call it d, let's say, it is the square root of x squared plus y squared plus z squared. And it doesn't matter which one I put in because I'm squaring. So I've got 12 over 5 squared. The signs will disappear, so it doesn't matter. And you can work with this algebraically. I can perhaps put it all over a common denominator, which looks like being 100 from that 7/10 there. So for the first term, I've got 12 squared, and I've got 5 squared on the bottom, which is 25, so I have to multiply by 4. And then I've got 5 squared, and I've got 4 on the bottom, so I've got to multiply by 25. And then I've just got a 49. So this ends up being, you have to just add all this up. I think I get 1,250 divided by the 100. And if you simplify that, just divide one by the other, divide through by 50 effectively, you get root 25 over 2. So that is 5 over root 2. And if you wanted it in decimals, it's roughly 3.54. But it's nicer to leave it exact, of course. And so this is the minimum distance from the origin to the point of intersection of those 2 lines that we were given at the start. And we've completed our problem.